Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And as you know, this is the decision analysis and data analysis and decision making 3 course under the NPTEL MOOC series, and as you can see this is the 6th week going on, which is the 27th lecture. And this total course duration, as you know, is total contact hours is 30, which is basically split and broken into 60 lectures, each lecture being for half an hour. And each week we have 5 lectures, out of which we have one assignment. So, we have already completed, if you see, that means we are in the 6th week, that means we have completed 5 weeks, 5 assignments, and in totality we will have 12 assignments. And after the end of this whole course, you will have a final examination paper, which will generally try to cover the whole of the concepts as you have utilized here. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we will still continue with the simplex duality and primal dual concepts. If you remember, we have been talking about slack surplus time and again. Now, when we come to the concept of slack and surplus, obviously that is being added in order to ensure that we have a basic feasible solution based on the fact that none of the variables are negative, because that would be infeasible, and as per the concept we consider all of the slack, surplus and the actual variables, decision variables to be non-negative, and when we attain the final solution, technically if nothing is wasted, nothing is used excessively or not wasted, the slack and surplus would be 0, the actual decision variables will be at the maximum value, and we will basically have the concept of getting the optimum value, maximum or minimum. Now, for the last problem which we are discussing, they could have been also of any sign, greater than or less than or some being equal to, but we discussed that if they are being equal to, we can break them up into greater than or less than, and basically have the demand and the supply constraints depending on the problem, where I said that you have different type of warehouses or factories onto the left, and you have different type of distributors, size being n or m, and n and m are not equal. All of the nodes in n are connected to all of the nodes in m, and obviously the demand supply would basically ensure that is less than type or greater than type, such that we can add the slack and surplus accordingly. Now, when we have the slack and the surpluses, and consider these slack and the surpluses are such that as there are 4 equations, we will basically have x 3, x 4, x 5 and x 6. So, I will basically mark them. So, obviously, you can understand, but I still mark them. So, x 3 is for the first equation, x 4 is for the second equation, x 5 is for the third equation, and x 6 is for the fourth equation. And obviously, their parameter values when they go into the objective function, whether maximization or minimization, are all 0. So, I will not mark it, but I am showing x 3 is multiplied by 0, x 4 is multiplied by 0, x 5 is multiplied by 0, x 6 is multiplied by 0. So, now if you look at this whole tableau, and I want to spend some time more into the tableau even I have not drawn, but you will understand what we mean by the tableau once we go into the next concept of the artificial one, because that will be important for us to understand. So, if you start with the basic solution, which is considered as the origin. So, obviously, x 1 is 0, x 2 is 0. So, in this equation x 1 goes, x 2 is obviously multiplied by 0. So, obviously, it will go, and x 2 also is 0, x 4, x 5, x 6 are not there. So, x 3 would be 1000, which is here. So, we will have the value of x 3 as 1000, x1 as 0, x2 as 0. When I go to the next equation, x1 is 0, x2 is 0, x3 is, even though it is 1000 is multiplied by 0. So, obviously, its effect will be 0, x5, x6 are all multiplied by 0 even if their values are non-zero. So, x4 is 1500 which is shown here. Now, when I come to the third equation, x1, x2 are 0. So, even if they are multiplied by 1 it becomes 0, x3 1000 but multiplied by 0 becomes 0, x4 multiply even 1500 multiplied by 0 becomes 0, x6 whatever the value is will come to that later on, is multiplied by 0 it will be 0. So, x5 is 1715. So, this is 1715 and the last equation x1, x2 are 0 because of the origin. So, 4, 2 have no effect, x3, 4, 5 which we have found out as 1000, 1500, 1750 what effect would be 0 because all the parameters are 0, and last is basically x6 which is the only variable left based on the last constraint, it will be 4800. So, when we basically start off the solution, we will have x1 0, x2 0, x3 1000, x4 1500, 1500, x4 x5 1750, x6 as 4800. So, the basic feasible solution where we start is 0 0 1000 1500 1750 4800 and the actual maximum value would be the first item, the first value x1 is 0 0. So, all these values are 0. So, obviously, you will have a maximum value of 0, then you start moving depending on the maximization or minimization concept which we have. Now, there would be some degeneracy condition in linear programming. We can have that in this problem also, but first I will show you the graphical concept why degeneracy occurs. Degeneracy happens in linear programming whenever more constraints are active and they are utilized than the minimum number needed to define a point. So, say for example, you have in a 2 dimension 2 equations, solve them, get the 2 points. So, they are unique solutions. Consider there are 3 equations in 2 dimension and trying to solve them basically gives you some redundant equations or some constraints which are active and too many of them are active. In that case, we will have the degeneracy. Degeneracy points would basically mean that finding out the unique solution would not be possible for those points. I will come to that again as I said with a diagram in a 3 dimensional case, because trying to draw a 4th dimension would be difficult. So, I have tried my level best to give you a 3 dimensional concept. Now, we know in the basic solution requires non-negative constraints. So, when you are basically solving a non-negative means because all the points where you start off the basic solution, whether the slack, surplus or the actual variables all should be non-negative. So, we know the basic solution requires non-negativity constraints to be active for the non-basics, but when non-negativity also happens, there are alternative choices for the basic sets we can find out. So, obviously, it would mean that there would be degeneracy from which point to start our basic solutions would not be clear to us. Now, let us see this diagram. So, I have tried drawing into the 3D diagram. Let us have a look. So, if you see at this slide, so the point I have not marked too many points because or else it will become cluttered, but I marked some A, B, C, D. What are those A, B, C, Ds? I am going to come that within 1 minute. So, you have the origin where the highlighter is now marking. So, I will mark it with let me use a other color because there are red points here. So, let me use the green one. So, this point is basically the origin. What is happening? Yes. So, this is the origin. And if I go on to the right, I have the x1 direction or the variable x1. If I go orthogonal on the top, which is the y axis generally in the Cartesian coordinate of the graph paper, that is x 2, and technically the point or the axis which is coming out from the blue dot, which is the origin towards me, is basically x 3. So, they are all orthogonal. Now, in a 2 dimension we have a line to basically or the corner points are basically the intersection of minimum of 2 lines. Now, in a 3 dimension they would be intersection of planes. I am considering the constraints are linear. So, they would be just simple planes. Now, the planes I have marked them as A. So, if I the plane A is basically a slanted, if I consider this room. So, x 1 is going on to the right, x 2 is going up and x 3 is coming here. So, x A plane is like this, slanted like this, and you have basically at some angle you have the B plane, you have the E plane. If you look at the diagram and what I am explaining, you have the A plane, B plane, you have the E plane. So, the directions may be different. You have the D plane which looks like a triangular one, you have the C plane which is just must at some angle to A, you have the F plane and the G plane. Now, they meet at different points, which is immaterial, and this overall area inside this plane, consider A inside these planes, is basically overall feasible region in which the actual sets of feasible solutions are. And as per the concept of corner point solutions, the corner points would be given where the planes basically meet each other. They can be more than 2 planes also. Now, let us consider that in this direction you have one equation, 2 equation for plane, a third equation and a fourth equation. So, x star point which is here is basically over defined. That means, there are more than needed number of constraints which will define the x star point, hence that is a degenerate point, that is why it is basically marked as x star in the red color. Similarly, find out the number of such at any particular point, number of edges which are meeting. Now, if you consider the point where you have A plane, B plane, D plane and E plane meeting. So, that point which is here, I should let me use a different color here. So, that point x double star is defined by more than the required number of constraints. So, hence it will also be degenerate. When I come to the points which is being defined by the planes F G, and obviously there would be some other thing below. So, I am considering the number of edges which is meeting. In a 3 dimension case there are 3 points meeting, hence this point which is x triple star in the blue color would be a non-degenerate point, and which is basically can be a feasible solution, and we will consider that to be feasible and one of the contenders for the optimal solutions in the search set, where when we do the search along the corner points for this overall space which we have, which we consider as the feasible region. Now, when I go to the 2 dimension one, technically if I have equations, say for example, let me, the color has to be different. Consider it is 2, 3 and this 3 x 1. I solve them, I get unique solutions. So, I have some x 1 and x 2, I solve them and basically proceed accordingly. Now, consider along with these 2 equations, I have another one Now, in a 2 dimension, if you want to basically, so these I am given example, I am not going to solve them. So, consider if we have equations where all of them active and they give us active in the sense they are giving us some solutions about the feasible region, and if we solve them and if we find that all of them active basically gives me values of x 1 and x 2 in the 2 dimension, which is definitely not required as per the norm. So, they would be degenerate in the sense they are not possible, and will not be considering those sets of points in order to start our solution for the simplex method, or when we are going to consider the basic feasible solution. So, what are the norms? Now, here what I have mentioned, any 3 of the 5 constraints. So, here I am, even though I have not been able to draw very clearly, but I will consider there are 5 constraints, which is A, D, G, F and C. So, these are the 5 constraints in the plane concept, which is there for extra. So, let us check whether they are these A, D, G, F, C. So, yes, you see A, D, G, F, C are the 5 constraints considering the lines of the planes. So, 3 of the 5 constraints would define, but we have basically 5 constraints. So, the points which will have x star, which is red in color, is degenerate. Thus, 5 minus 3 or these 2 basic variables would have basically value 0, which means the solution is degenerate, because when we solve the problem technically in the actual solution, they would basically be 5 such, considering the slack or the surplus what we have in the 5 dimensions, and we are able to draw it consider. So, we would not basically have solutions which would be actually possible. So, it will degenerate to a degenerative point which would not be utilized for our solutions. Now, when we consider x double star, so x double star has A, B, E, D 4 surfaces and their points is given by x double star. So, any 3 of the 4 constraints, which is A, B, E, D, would define x double star. Hence, 4 minus 3, because 4 constraints are there and 3 is basically what is minimum number required. There would be one basic variable which will basically have a value 0, which means the solution is degenerate. But if we come to point x star, so obviously there would be a surface below x triple star here. So, it will be F, G and consider this H. So, if we have basically 3 constraints or planes and the solution basically gives the unique point, that would be non-degenerate point, and because in that case there would be 0 number of basic feasible solutions which are 0, and we can utilize that to consider as the starting point for our search technique for the simplex method. So, again I am drawing the diagram, but I am now going to concentrate on x triple star, which is blue in color. So, the third plane, or if it is in 2 dimension, the line has not been shown, but the planes are F, G and the other one which is H. Okay, so it has been mentioned as D. Okay, since D is not right, so technically it would be H, sorry, my mistake here. So, because we are considering that D, if it comes out and meets the surface at this point, but it has not been drawn. So, I will basically change it to surface H, which is below. So, surface H is this one. So, if I marked as a yellow green or something. While F would be this one, and G would be, they look in the 2 dimension, but they are just slanted planes, straight obviously, but slanted planes. It is like this, corner points here and the surface here. So, the corner point which is here at this point is x triple star. So, 3 of the constraints D, G and not D. So, this will go, this will be H G and F will define the point x triple star. Thus, 3 minus 3, because there are three constraints, there are actually variables which are required is 3. So, 3 minus 3 is 0, variables will have value 0, which means the 0 number of basic variables have value 0, which means the solution is not degenerate and can be considered for our concept of as one of the contributors in the basic solution. Now, in the standard format of the simplex method, which is of size m cross n, and we will consider the m being the rows and n being the columns, which if when you consider from the constant point of view the solutions. So, m would be number of constraints, n would be the number of variables, including the actual basic variables, slack, surplus, and also later on we will see the artificial variables. And obviously, if you and it does not mention anything about the numbers of m or the numbers n, it only defines what is m and what is n. So, for the matrix A, the number of rows is m as in mangoes, n as in nose, or m as in Mumbai, n as in Nagpur. So, the number of maximum bases which is possible would be given by factorial n divided by factorial m into n minus m, and based on that you can basically proceed to how you can find. So, it is like this, how you divide the whole set. So, you can basically divide the whole set into m number, and then left would basically be n minus m. We are trying to basically consider the total number of combinations which is there. Now, as I mentioned, we have already considered the slack and surplus. So, we will basically go into the history of a little bit about the artificial one. Now, we have been talking about the artificial variables time and again, but the point is what are the artificial variables and why. Now, if you remember the background for the slacks and surplus, it was basically the constraints being of the type greater than and less than, and they were basically related to the production or the supply. If you remember the n number of distributors or n number of warehouses or factories on the left hand side and m number of distributors on the right hand side, and all being connected. So, whether connection is at all available, that is a different question, but we will make the connection available between each of these n nodes and each of these m nodes. Now, whenever we start considering the slack and surplus, we intuitively assume that if I consider the problem where the actual variables are 0, that is at the origin, the slack and the surplus would obviously come out automatically to be positive, and they can be considered as the basic feasible solution from where you can kick start your simplex method. So, if I consider, I am going back to the solution, generally I do not scroll up, but I will just give you that. So, if you consider this problem, they were either of the less than type. So, obviously, you had the plus values of x3, x4, x5, x6. If they were greater than type, that minus sign would just be taken initially, and then you can reverse the minus sign to a plus sign, considering that how the change of the signs can be done on the right hand side and the left hand side of the equation. Now, when I am talking about the basic solution, which I did mention, but when I was considering this problem. So, the tableau, when you have the A matrix, there would be a set of identity matrix inside that A, which will give the initial values corresponding to the basic solutions from where I am going to start. So, initially this would be, if you remember, this is 1 0 0. So, on the left hand side you have x 3, then the next point in the tableau, in the next row you have x 4, which are actual solutions of basic feasible solution at that point when you are going to start. The third variable would be x 5 and the fourth one would be x 6, and x 1 and x 2 are not there. So, the next column is 0 1 0 0. So, that is the vector. So, 1 0 0 0 0 1 0 0 the third one is 0 0 1 0, and the fourth one is 0 0 0 1. So, let us see what we actually mean. I will use a red color because red color is not there. So, it would not be confusing. So, I have here x 3. Now, let me use this is x 3. Can you read it? It is very difficult to read. So, I will erase it and use the black one. So, this is x 3, which is corresponding to the first constraint, x 4, x 5, x 6. So, when I solve it, the matrix when you multiply, so on the this x 3, x 4, x 5, x 6 are on the right hand side, which is basically x vector, and the a values are, if I go along the row, 1 0 1 0 0 0. So, when I multiply, obviously the and obviously in the values of x 1 x 2, technically they are actually 0, they are forced to be 0. So, it will be 1 into 0 plus 0 into 0 plus 1 into x 3 plus 0 into x 4 plus 0 into x 5 plus 0 into x 6 is 1000. That is why I am getting the value of x 3 as 1000. Next, when I multiply, x 1 x 2 are at that corner point, which is the origin are 0. So, it will be 0 into 0 plus 1 into 0 plus 0 into x 3, because x 3 whatever the value is, we have found out 1000, it does not have any effect. So, 0 into x 3 plus 1 into x 4 plus 0 into x 5 plus 0 into x 6 is equal to 1500, hence we get x is 4 is equal to 1500. Similarly, in the next third in the third constraint, it will be 1 into x 1 is 0. So, it goes 1 into 0 plus 1 into 0 plus 0 into x 3. So, it vanishes means it does not have an effect. 0 into x 4 obviously does not have an effect. 1 into x 5 plus 0 into x 6 is equal to 1750. So, you get the value of x 5 as 1750. Last equation being 4 into 0, obviously value is not there, 2 into 0 value not there, 0 being there for x 3 does not have any effect, that means it is not there, 0 into x 4 does not have any effect, 0 into x 5 does not have any effect, 1 into 6 x 5 gives you 4800. So, the overall value of x 6 is 4800. Now, this may not be possible, and we basically bring the concept of artificial variables. Why this is not possible? Let me basically go through an example in the next class, which means with this I will end this lecture, which is the second lecture in the 6th week, and I will basically start off discussing the concept of artificial variable, how they help us in trying to get basic feasible solutions in the discussion. Now, you may be asking that why do we need artificial variables? If there are equality constraints, and obviously technically no slacks and surplus have to be added, obviously you can add it by a greater than equal to and greater than sign and less than sign, that is a different question. But we do not have any slack and surplus, that means we do not have any set of variables like as we saw it here, which can be put into non-zero, greater than 0, that is non-negative, and can kickstart your own simplex process. If we do not have that situation, that luxury for us, we actually need the artificial variables. And what is the actual effect in an objective function, we will also see that later on. With this, I will end this class and discuss the artificial variable concept in the later class. Thank you very much and have a nice day.